Okay, covalent bonds. The Lewis structure for molecular compounds shows them as atoms next to each other sharing electrons in order to get octets, or duets for the little tiny guys. When you have two nonmetals, you don't have one that's willing to get rid of its electrons, to totally give them. And so in order to form octets, they share. So let's look at water and chlorine and see how Lewis structures can show the bonding that occurs there. So water. Well, water has an oxygen atom. How many valence electrons does oxygen have? 6. So we can represent oxygen as O with 6 dots around it. And hydrogen has how many valence electrons? 1. So there's a hydrogen atom. And we're going to put another one over here. So trying to get octets, or for hydrogen, a duet, right? They're trying to be like the nearest noble gas. So for hydrogen, he's just aspiring to be like helium. 2 electrons would make him happy. So hydrogen's begging oxygen to give him an electron. You've got so many electrons, just give me 1, you can spare it. And oxygen's like, no way, I want 8, and I'm not going to give up any. So they can't agree on this. They decide to share. So they're going to share those 2 electrons. When you share something with someone else, it essentially belongs to both of you, right? I share a house with my husband. It's my house and it's his house. It's our house. These shared electrons belong to both atoms. So hydrogen looks at himself now and says, I have 2 electrons. I'm good. Oxygen looks at herself and says, I have 2, 4, 6, 7 electrons. Not quite there. She's going to look for another hydrogen atom to share with. And here's another hydrogen atom. And so she's going to share that electron with hydrogen. So now oxygen counts the shared electrons and these electrons that belong solely to her. And so you've got 2, 4, 6, 8. 8 valence electrons for oxygen in the water molecule. That's a good thing. Hydrogen counts the shared electrons, says, I've got 2 electrons. This one says, I've got 2 electrons. Hydrogen's a little guy. He can't handle 8 electrons. He's just trying to get 2. So everybody's happy. So water is a stable molecule because the oxygen and the hydrogen are lowered in energy when they form a water molecule. Let's look at chlorine. So here's a chlorine atom. How many valence electrons does chlorine have? 7. So we're going to have 1 unpaired, and we're going to have 6 that are paired up. And that's how we would put 7 electrons around. We're going to do top, bottom, right, and left instead of like making a circle, because when they're in a circle, then you have to get your finger out and count, and that's no fun. So chlorine would like to get 1 more electron. And if sodium was around, sodium would say, yeah, you can have this, and they'd form an ionic compound. But what if sodium's not around? Well, if there's 1 chlorine atom, there's going to be another one nearby. So here's another chlorine atom. This one also has 7 valence electrons. They can't agree on who should give the other an electron to make them happy, and so they share. So they each share 1 electron with the other. So this chlorine looks at herself and says, well, the shared electrons belong to me. 2, 4, 6, 8. I'm good. This chlorine says the shared electrons belong to me also. 2, 4, 6, 8. I'm good. This is why chlorine forms a diatomic molecule instead of being individual chlorine atoms. Because by forming this molecule, its energy is lowered. Any questions? So, identify bonding pairs and lone pairs, also known as non-bonding electrons. So when we look at water, this is a pair of electrons that's forming a bond. They're shared between the atoms. So this is a bonding pair right here, and this is a bonding pair. How many bonding pairs are there in this chlorine? Just one, right? The one bonding pair. There are other electrons there that are not involved in bonds. And these are called lone pairs because they're by themselves. It's a pair of electrons that's not being shared between two. It's just on a single atom. Oh, what color should we make those? Running out of colors. Well, I did use orange. I'll go for black. So this is a lone pair, and this is a lone pair. Here we've got lone pair, lone pair, lone pair, lone pair, lone pair, lone pair. So we've got 6 lone pairs in this chlorine molecule and 1 bonding pair. In the water molecule, how many lone pairs? 2. 2 lone pairs. How many bonding pairs? 2. Any questions? Yeah.
What would the bonding of nitrogen look like?
We'll get to that.
Okay.
What would the bonding of nitrogen look like? Yeah. Because nitrogen also forms a diatomic molecule, but it wouldn't work out just like this. Any other questions? So this is what's known as a single covalent bond because we're sharing a single pair of electrons. So that's a single bond. And we often represent it with just a line. So this is, without the circles and the arrows, that's the Lewis structure for water. We will often make it a little simpler and just draw the bonding pairs as lines and then the lone pairs as dots. Because when you're doing this, I'm using the marker and I'm making it fat so I can just go dot, dot and get nice sized dots. When you're using a pencil and if you just stab at the paper, you get this little tiny dot that's hard to see. And so in order to make them visible, you've got to scribble and make these little circles, and it gets really tedious, right? So this is also the Lewis structure for water. And what you have to remember is that each line has an electron at each end. It's a pair of electrons, okay? So let's look at double and triple bonds because we can share, we can share, I forgot to make a phone call. Oh well. We can share more than a pair of electrons. Okay, so let's look at oxygen, or hey, let's look at nitrogen first since someone asked about nitrogen. Let's do nitrogen first. Well, I've got a black pen here, so we'll just use black. So nitrogen, how many valence electrons? 5, right? So we could illustrate that like this. And then another nitrogen over here, also with 5 valence electrons. I'm drawing the dots as I'm drawing them just to make them convenient for what I know I'm going to do. So 2 nitrogens, we know it forms a molecule of 2 nitrogen atoms. How can this work? We've got to get 8 valence electrons, an octet for each of these. Well, we could share electrons, right? Is that going to satisfy everybody? No. A triple bond will. So they're each sharing 1 electron, and that's not enough. We need to share more. So let's share another electron with the other atom. We're getting closer. So they're going to each share 3 electrons with the other atom. Now when we look at this nitrogen atom, it counts all the shared electrons as its own, 2, 4, 6, plus these 2 over here makes 8.
The
model kits, it looks really cool when you actually do it.
Yeah, it does. Yeah, we've got model kits, the ball and stick model, and you're welcome to play with those anytime you want, and I will use them as illustrations sometimes. It really helps you to get an understanding of what's going on. So this is kind of an awkward drawing, right? So instead of showing all of the dots, what we typically will do is we'll draw the element symbols. This is a triple bond because we've got 3 pairs of electrons. 1, 2, 3 pairs. And then we put the lone pairs in there. So each nitrogen, you count these lines as 2, 2, 4, 6, 8, octet. This guy, 2, 4, 6, 8, octet. Good? The electrons that are shared count for both. So as it turns out, we didn't plan it this way, but kind of convenient. My husband, who's also a chemist, and I have 6 children. They belong to both of us, right? So we have 6 children shared between us. That would be a triple bond. You like that? I'd like to say we plan things like that, but no, it just kind of happens. Let's look at oxygen. So there's oxygen. How many valence electrons? 6. So 2, 4, 5, 6. Draw another one over here. 2, 4, 5, 6. So 2 oxygens, we're going to put them together so that they can share and try to get 8 valence electrons. So share 1 electron pair. Each share an electron with the other. Doesn't quite do enough. So they're going to share another electron. And now they each have a total of 4 electrons from the shared ones and 4 from their lone pairs, so they each have 8. And we would draw this as an O with 2 lines to an O. That's a double bond, 2 pairs of electrons being shared. And then we'll put the lone pairs, also show those. So that's a double bond. Any questions? So let's compare this to reality. Let's look at the Lewis model for water, for H3O, H3O plus, and H2O2. So, different combinations of hydrogens and oxygens. Well, we've already done the Lewis structure for water, so we're not going to go over and over on that. We'll just draw it out here. So there's water. We know that water is stable. It hangs out all over the globe and doesn't, do a lot. It's water. It evaporates, it freezes, but it stays water. It doesn't react very much. Oxygen has an octet. It counts 2, 4 from the lone pairs, 6, 8 from the bonding pairs. Each hydrogen has 2, a duet, and so everybody's happy. What if we throw another hydrogen in there? So here's hydrogen, oxygen, hydrogen, and we stick another hydrogen in here. That hydrogen has an electron, and he's like, I want in, and kind of forces himself in, and so oxygen's, well, I guess I'll have to share one with you. Would you predict that that's going to be a stable molecule? Does that satisfy the octet rule, where things are going to have 8 electrons, or the little guys are going to have 2, the duet rule? No, oxygen there has 9 electrons. That's not good. So H3O doesn't happen. It's unstable. If it should happen, it's going to fall apart very quickly and make something that is stable. What about H3O plus? So here we've got H3O. How would that become a positive ion? By losing an electron, right? Well, so let's let's get rid of an electron. Now, overall, this has a positive charge. Do you think that's going to be stable? Does oxygen have 8 valence electrons? Yeah. Does each hydrogen have 2? Yeah. So this satisfies the octet rule. Lewis' theory says that's probably stable, and it is. Let's look at H2O2. So there are the Lewis, kind of messy, but Lewis symbols for the different elements. So oxygen can share an electron with that hydrogen. Hydrogen's good. This oxygen's like, well, that's not quite good enough for me. I need to share an electron with this oxygen. So now this oxygen on the left has 8 electrons. And then this oxygen still needs 1 more, and so it's going to share with the hydrogen. So we could show that this way. Does that satisfy the octet rule? Yeah. And so we would predict that H2O2, hydrogen peroxide, is stable. It's not as stable as water, but it is a stable compound. You can buy it at the grocery store. Yeah.
Can we just make it a triple bond if we want to do it? It breaks the rules.
Well, you can try making a triple bond with these guys, but you're not going to be able to satisfy the octet rule. Yeah, so for most of the things we look at, there's really only one way to make them. Because hydrogen only has 1 electron, so it can always only form 1 bond. So you can't make a double or triple bond with hydrogen. And if you try to do a multiple bond here, well, you can do a double bond between 2 oxygens, but then you don't have room to share electrons with hydrogens, and so you just have an oxygen molecule. And you can't get a triple bond because then you'd have too many electrons, and that's not possible for oxygen. Any questions? So does this mesh up with what we observe in terms of properties? It does. So covalent bonds are highly directional. That pair of electrons is shared between 2 particular atoms. It doesn't go all around in 3 dimensions like the ionic bonds do. So highly directional. So these covalent compounds are going to form discrete molecules. Did you remember that lab where we made, what was it, zinc iodide? And there was that question that messed everybody up. Can you get a molecular formula for an ionic compound? You can't, because in an ionic compound, you have alternating ions, and they're just all arranged in a big lattice. There is not a specific molecule. In a covalent compound, you do have discrete molecules. So here we have, what is that? Pentane. Carbons and hydrogens. And we've got covalent bonds holding the carbons and the hydrogens together. But there are not covalent bonds between this molecule and the next molecule. There are what are called intermolecular forces that have some attraction between the molecules, but those are very weak. And so we observe that because of those weak intermolecular forces, covalent compounds tend to have lower melting points and boiling points. They're much more likely to be a liquid or even a gas at room temperature, whereas solid compounds are always solids at room temperature.